Hello again. This is Roger Kochbar, and this is Bioelectricity Week 2, Segment 4. In this segment, we're going to talk about the pumping action in particular. So in this slide, I have shown in the top part the results of the pumping action in frog muscle for potassium. After pumping has reached a steady state, the concentration of potassium ions in the inside of the cell is 124 millimolar. On the outside of the cell, it's only 2.2. That's what the pump did. Similarly, in this cell, on the inside, the concentration of sodium ions is 109. The concentration inside is only 4.0. These are just amazingly different values. It's not just a little bit off, it's off, hugely off. Not just 10%, but hundreds of percent. How does this happen? And the answer is little teeny tiny sodium-potassium pumps that are scattered all through the membrane. So I made a sketch at the bottom of this slide where the pump is simply indicated by this X shape. So here's a pump. Now the X shape is way out of proportion to the membrane. Membrane is just shown by this thin line. But the pump is pretty much contained within the membrane. I've drawn it too large here, simply for purpose of illustration. What does the pump do? Well, what the pump does is it attaches itself, it expends metabolic energy, and on the inside it looks around for sodium ions. Sodium ions, and the goal of the pump is to take the sodium ions from the inside here and to fling them out of the interior into the exterior. They don't want to go out there. Diffusion would bring them back in because there already is a lot of sodium outside. They want to stay inside, but the pump grabs them, grabs those sodium ions and just flings them out. At the same time it is doing that, the pump is attaching to potassium ions, which are outside, if it finds some outside, and it's bringing them around into the interior. So the potassium, which does not want to go into the interior, is brought into the interior nonetheless. Well, that's how it works. It's like separating the boys and the girls. The boys and the girls may not want to be separated. But in this case, the pump grabs one of the boys and flings him outside. There he goes. Then at the same time, it grabs one of the girls and flings her inside. The membrane then is the wall by which they are separated, and the pump is the police that ensures that that remains the case. It's a forceful and vigorous mechanism because the gradient is high, and really, truly, the natural process here would be to put things to mix everything up so that there were about equal concentrations of potassium inside and outside and equal concentrations of sodium inside and outside. But it's not what happens. Let's just look at the numbers once again. So in squid axon nerve, potassium inside 397, outside only 20. Sodium ions inside only 50, outside 437. The pumps have been doing a good job catching those ions that are in the wrong place and flinging them over in the other direction. So the result of all this pumping is taking place all the time from the moment of conception until the moment of death. And these pumps, there are billions of them in each of us. They are pumping. And their job is to keep these concentrations unequal, because these unequal concentrations are what's going to drive the membrane in such a way that it can have voltages. So this closes our segment. In the next segment, we'll come back and talk about this topic some more as to what the concentration differences are useful for.